Thank you very much. The next panelist is Professor Paul Chu, superconductivity above 100 degrees.
It's a little bit tricky, huh?
See, the next panelist is Professor Paul Chu, superconductivity above 100 degrees.
Thank you. Thank you. I think it's okay. Yeah, it's okay. I think I would take this opportunity to first thank Alex Miller, George Batnos for bringing across all this problem. And then I would also like to thank Barry Matthias, of course, he's not here now, and also Art Slate, who brought me to, gave me the interest, made me interested in the superconducting oxides. And also for John Bardeen, Marvin Cohen, Ted Jabor, and C.Y. Huang for their belief in non-conventional superconducting mechanism. And also Art Freeman, for his enthusiasm, constant enthusiasm, and also for his valuable information concerning band structure calculation. Of course, the support from National Science Foundation and NASA, and also University of Houston are greatly appreciated, especially for those colleagues at NSF who are making the so-called flexi time schedule of the federal government more flexible to accommodate my erratic working schedule between Houston and Washington, D.C. And last but not the least are my colleagues and students for their many sleepless nights and also hard working. Because of time, I just show this, mainly the group at University of Houston and University of Alabama at Huntsville, headed by Professor Wu, and also Lockheed Research Center, C.Y. Huang, and also Los Alamos National Laboratory, Chern Gibble, and Joe Thompson. And also particularly, I appreciate the collaboration with a geophysicist from the Geophysical Lab, Dave Mount, Bob Hazen, and other people. I think the whole thing started, as I mentioned previously, because after we recognized the existence of the Swiss results, we decided to reproduce the result. Indeed, it was superconducting at around 35 degrees. So we decided to see what's happening there. So we decided to apply pressure, and also by changing the chemicals substitutions, we found that the pressure effect was extremely unusually large. And then immediately we decided to simulate the pressure effect by substituting a barium with strontium, which has smaller radius, atomic radius. Immediately the TC went up without the application of pressure. We thought just by squeezing it, the TC would go up to much, much higher. But unfortunately, when we replace barium with calcium, which has even smaller atomic radius, the TC goes down. So this tells us there exists an optimum interatomic separation for high TC. And then the other hint, by that time, by the beginning of this year or the end of December, we accumulated quite a bit of data. We found out that the TC usually, the onset TC goes down when you make the material purer in the so-called layer structure, and also when the width of the transition goes down. So this tells us something. And then there's also, by that time, we have observed lots of indication of superconductivity as at temperature higher than 70 degrees, but only in those material without the layer structure as the main phase. Let me just show you this curve, original curve measure on November the 25th. You see the resistance drops all the way starting from 70 degrees to 50 degrees, and this was mentioned in our first paper. And then we continue on. We decided in order to look for higher TC material, we have to go into... I'm sorry. We decided for TC higher than 70 degrees, we should go into compounds with structure different from K2NiF4. In fact, here I can also show you another compound which shows magnetic measurement starting 100 degrees. I purposely turned it upside down. And going like this, starting from 100 degrees. But unfortunately, this signal disappears after a day or so. So then we decided to look for a new compound. Unfortunately, on January the 28th, and this was observed. And Professor Woods tried to impress people. In fact, he only measured it down to 77 degrees by using the liquid nitrogen duo. As you can see, resistance really goes down. And immediately following that, we improved the temperature at the samples slightly, and right now, the resistivity at that time, a few days later, we got the onset at 98 degrees and goes down to 0 at 94 degrees for the yttrium, barium, copper oxide. As you know, at that time, by this time, we also went to measure the critical field. The Meissner effect, in fact, with the Los Alamos group and also Lucky, C.Y. Huang, and our group working together, and that was the first time measuring the DC Meissner effect, confirming that this is indeed a superconducting transition. And also from our preliminary study, it shows that this structure is different from the characteristic of this material is different from the so-called layer structure. And so now, unfortunately, at that time, our sample has two phases. One is black and the other is green. And then by the end of February and also the beginning of March, working together with the geophysical laboratory, especially Bob Hazen and Dave Mao, who have extensive experience handling dirty samples like rocks. So they separated and identified the phase. The superconducting phase indeed was the black phase, has a composition expressed here with x less than 3. And it has a tetragonal symmetry. And the non-superconducting green phase has this kind of formula with the orthorhombic symmetry. And let me just show you, because Dr. Hazen is going to describe the structure later, let me just show you briefly. This is his view graph here. As you can see, you have layers something here. I'll come back to this structure later when we discuss the occurrence of superconductivity here. Now, with all that, we decided to find out what is the active elements, components for superconductivity above 90 degrees in this class of material. And so we decided to replace all these elements, A elements, by all this whole bunch of elements. And we found that basically the TC is almost constant. And here's the table of all the TC. The TC basically, TC0, the onset temperature is between 91 to 98 degrees. And then the resistance goes to 0 between 70 to 94 degrees. I believe the 70 degrees can be improved later. And then also look at the linear deviation. The deviation from linear temperature dependence of resistance starts as high as 160 degrees. And if you want to define that as the onset temperature, certainly you may. And then we also found all this material becoming superconducting. And then when we measure the diamagnetic shielding, AC shielding, it goes from 97 to 100% now with all this material. So from this study, we realized that superconductivity is independent of A atoms. And then when we look at the structure, they are quite interesting because they have the layer structure. Actually, it has CO2, that kind of, this kind of structure. I think it's what I would like to show this, very interesting, because if you look at here, I did not put down the 6 plus x. The x I haven't put it in. And basically, if we only look at x without, only 6 without the x, and that's the structure. And the most interesting part is this. When we look into the lanthanum, barium-2, copper 04, the layer structure, and this is the structure. And you have layers of copper and CO2, copper, oxygen, 2 layers going like this, here and here. And they're separated here. According to band structure calculation of Lenny Mattis and also R. Freeman, they're not coupled. And here we have 3 here, okay? Well, and then 3 units up here. And then when we change this A elements, it has no effect on superconductivity. Perhaps now we can consider that superconductivity actually is confined in this region. Okay. And the interesting part is this. If you look into that, in the layer compound, we have 1 layers. They're not coupled. And then in the new compounds, it has 3 layers. One layer has 30 degrees, and 3 layers has 90 degrees approximately. Is this accidental or not? We don't know. But certainly, those 3 layers are coupled through the barium. And whether that's true or not, it has to be determined. But so based on this result, we think maybe we need bigger layer assembly and to get to higher temperature. And I would like to emphasize at this point, there are indications of superconductivity at 120, 150, 240. In fact, I should mention the 240 drops of resistivity at that temperature, not only observed by us, but also observed by by the Berkeley group, Marvin Cohen and Alex Zetto's group. Do I still have time? Okay. So now, with all that results, what are the major ingredients in the superconductivity of this class of material? It appears to us right now all these structures have some defects, and therefore there must be local deformations associated with defects in here, so it must be important. And the second thing is all that assembly of layers over there, it retains some kind of quasi two-dimensional characteristic, because when you change the A elements, you don't change the superconductivity. So it indicates that perhaps those three layers do not really couple strongly. It retains some two-dimensional characteristics. And also, in the potassium nickel fluoride structure, where the barium and the A atoms are not really ordered, they are disorderly arranged. But here they are ordering, okay, and arranged in the 90 degrees one. So with all this, it appears to us, as already Dr. Miller already pointed out, perhaps in this class of material, we need some new kind of superconducting mechanism, and mainly of electronic in nature. So then what is it? It appears to us it's due to the coupling of electrons through the virtual exchange of excitons. And the excitons, if we look into there may be generally grouped into two types. One is the excitons and charge carriers are in different spatial regions. In order to accomplish that, we're talking about interfaces. Interfaces can exist both in a compound system with two different structure phases, or even in the same phase. Okay? If we look at the layer structure, we may accomplish that kind of situation. And this kind of model has been previously proposed by Bardeen and co-workers, and also Ginsberg, and also CST, my colleague at the University of Houston. Now, what would happen in the other case, where the excitons and charge carriers in the spatial regions, in the same spatial regions, okay? In that case, then we can make use of the so-called plasmons mechanism, which has been proposed by Crescent of Lawrence Rady LBL, and also John Ruwald of Virginia University. According to their models, two-dimensional plasmons, acoustic plasmons, can help us to achieve higher TC. But then what about the charge? Because when you look into this layer, the coppers charge are transferring between different states, and therefore Chandra Varma proposed a charge transfer fluctuation situation where you can get an enhancement in superconducting interaction. And then the other type is perhaps when you look at all this material, they all have some magnetic origin in it. The subtle, as we observed previously, the material lanthanum copper barium oxide, you can make it into insulator, you can make it into superconducting, you can also make into magnetic situation, or magnetic compound. So here we are talking about a possibility of spin fluctuation associated with the copper 2+ ions. And that can enhance superconductivity and get a D-pairing, just like people proposed in the heavy fermion situation. And then the other model is resonating valence bound state proposed by Phil Anderson. And it appears to us at this moment, and there's no experiments which can distinguish one from the other at this moment or rule out any of this, and I think they all deserve some attention. Now, one final conclusion. Can we get TC higher? And I believe we will be able to get higher TC. And let me just show you one of the curve here, which is just an indication of superconductivity. In fact, we have cited this kind of drop in resistivity more than 15 times now, and we hope with the hard work of everyone, we can stabilize that phase. Thank you.
Thank you very much, Paul.